Okay, I hope you're all good. We're going to do some work today on friction, which is linked to the video that I set you guys to watch at the end of last lesson, looking at dynamic and static friction. So I'm going to go, first of all, through kind of some of the key concepts I want you to understand. I'm going to show you a little simulation, which I'll also link in the Google Classroom post so you can have a go at it yourself. And then I'm going to be asking you guys to do some questions based upon this. They're quite difficult, but hopefully you guys are up to it. So static and dynamic friction. Remember, static friction is the friction acting on an object when it's not moving. So you push on a car that's sitting on the road. If that car doesn't move, then the force of you pushing is being opposed by a frictional force. We call that static friction. If you push something and it does move, if you can get that car rolling, then you're going to have dynamic friction. Okay. So just to begin with, let's say we've got a book sitting on a table. The book weighs 5 kilograms and it's got a value of static friction of 0.5. Okay, we call it a coefficient of static friction. It's always a value between 0 and 1, and it depends on the nature of the surfaces involved. So this would depend on the nature of the table and on the book. Okay, if I put the book on a different type of table, that coefficient of static friction might change as well. So it depends upon the nature of the surfaces themselves. So let's say I come along and I push on that book with a small force, let's say 10 newtons. Now, because that force is quite small, it's not going to move the book, okay? And therefore, I know that there must be an equal force of friction acting back on the book. So I decide, let's push it a bit harder. Push it with 20 newtons. Still, frictional force acting back is 20 newtons. The book doesn't move. So what I want you to get from this is the frictional force doesn't have a constant value. At least the static frictional force doesn't have a constant value. Okay. However much I push on that book, it will push back on me up to a limit. Now, what is that limit going to be? Well, the limit is going to be given by this equation here. Now, in your data book, you guys are going to get given for the exams, rather than an equal sign here, it's going to say that the friction or the static friction will always be greater than or equal to the coefficient of friction times R. Okay. Now, R stands for the normal reaction force. Okay. So if you know the normal reaction force, okay, which is the surface pushing back on that book in this case, you times it by the coefficient of static friction, okay, then the frictional force will always be either greater than or equal to this. So if I push on it with 10 newtons, that's not as great as the maximum frictional force. Okay, but when I get up to the point where it's just about to move, I can replace the greater than with an equal. So it's basically saying when I get to the largest value of static friction, okay, it's going to be equal to this mu value, this coefficient of static friction, times R. So how do we work out normal reaction force? Well, in this case, it's quite simple because we're looking at a horizontal surface. The table is horizontal, and therefore the normal reaction force will balance the weight. We know that because if it doesn't, then either the book will be pushed up into the air or it will move through the table. Now, we know when we put things down on tables that they generally stay stationary, so we know that it must be in what we call translational equilibrium. That means zero resultant force, forces are balanced. Okay, so let's do a little bit of maths. Okay, I know that the normal reaction force is equal to the weight. Weight is mass times acceleration due to gravity. Let's plug the numbers in. So we've got a mass of 5. We're assuming this is on Earth, 9.81 as g, and we get 49 newtons as the weight. So 49 newtons is the weight. It's also going to be the normal reaction force. So I can use that to work out the maximum value for static friction, because it's just going to be the coefficient of static friction times the normal reaction force, okay, using this equation here. And so I get this value, which is 25 newtons. Now, what that basically means is if I push on that book with up to 25 newtons, the friction will match it and it won't be able to move, okay? But if I come along and push with greater than that maximum value of static friction, okay, then the static friction can only, okay, counter 25 newtons of that, okay? And so now the object's no longer in translational equilibrium, the forces are not balanced, and it's going to accelerate. So any force greater than 25 newtons applied to that book is going to cause it to accelerate, okay? So this is the kind of basic idea behind friction. You push on things, okay, friction will push back, okay, but it will only get pushed back with the same value you push up to a point. Now, often we show this on a graph, and the graph I've got on the screen here, on the x-axis is the force applied to the object. So this is me pushing on the book, okay, and on the y-axis is the frictional force. Now we've got a nice straight line here, not just a straight line, but actually my y-axis at this point is equal to my x-axis. Push on the book with 10 newtons, friction is 10 newtons. If I push with 20 newtons, friction is 20 newtons. Now, this relationship where the static frictional force is equal to the applied force will continue up to a point, and that point is my maximum static friction. But what about after that? How's the graph going to look when it actually starts to move? You see, I've put this as the static region. To the right, we're going to have the dynamic region where it starts to move. But is it simply going to be that the value just stays the same? Well, no. Okay, we've got something more happening here. So we know that the maximum static friction is equal to mu s, the coefficient of static friction, times r. We've also got a similar equation for dynamic friction. Now, these will both be in the data books for exams. You don't need to remember them, but they're both just labeled as F for FF for frictional force. So you need to know that the one with the coefficient d, mu d, is for the dynamic friction, and the one with mu s is for the static friction. Now, the second one, there's no greater than or equal to in it. It's basically equal because frictional force, the dynamic frictional force, is a constant. If you keep an object moving, it doesn't matter how fast you push it, okay, how fast you make it go, your force required to overcome friction is always the same. But one key thing about these kind of mu values, these coefficients, is that the coefficient of static friction is always greater than the coefficient of dynamic friction. Okay, and what that basically means to us is that the maximum force of static friction, okay, is always going to be greater than the maximum force of dynamic friction. Okay, you've seen this for yourself, I'm sure, when you push things and some things it's hard to get them started, but once you've got it moving, it's actually easier to keep it going. Okay, so you have to push more to start it than you do to keep it going. And we see that on the graph because this is what the rest of the graph is going to look like. As I push in the static region, as I push on the book, it pushes back exactly the same, pushes back exactly the same, pushes back exactly the same, until I get to the maximum value of static friction. And then the object will start to move. But as it starts to move, the frictional force drops to a new constant. Now, this is now my dynamic friction. And it doesn't matter how fast I make it go, okay, the frictional force stays constant. So it's not like air resistance. With air resistance, the resistive force depends on the velocity. If you go fast, you get more air resistance. Well, once you get the object moving and you've got dynamic friction, that value is a constant. It doesn't matter how quick you're moving, okay, the friction is going to be a constant value. So these are a couple of key things I want you to know. I want you to be happy with these equations in the top left corner. I want you to understand what this graph means, okay? But we have to deal with something a little bit more difficult, and that is objects that are not just on horizontal slopes, but are on inclined slopes. So an inclined slope, or an inclined plane, okay, I basically just mean a slope. I'm just going to come off this PowerPoint for a minute. We're going to go back on for a second. And I want to show you this simulation that I found, because I think this is quite good. I think this is quite good for helping to understand what goes on when you put an object on a slope. Now, when I go on this, I'm just going to kind of make this a bit simple. I'm going to make it on the Earth to get rid of one of these things. I'm going to make the starting velocity 0, just to keep things nice and simple. Can I make it 0? Oh, it's hard to keep it there. Hang on. Can't seem to. Oh, can't be that hard. Maybe it can. Oh, it was there for a second. There we go. Okay, so I'm going to give it an initial velocity of 0. Okay, so it's basically stationary to begin with, and I'm going to make the angle 0 to begin with. I'm also going to take off these components here. I'm going to put them back on in a minute. Now, the idea here is that at the moment, the forces acting on this object are balanced. So we've got its weight acting down, and its weight will be equal to the normal reaction force. Now, as I change the slope, notice what happens. Okay. As I change the slope, suddenly the third force appears, and that force is the frictional force. Okay, so now we haven't just got the weight and the normal reaction force, we've got the friction too. Now, if I go back to the original on the horizontal slope, the weight is equal to the normal reaction, like it was in the example I gave you earlier. But you see that when I put it on a slope, these two forces are no longer the same size, okay? And actually, if I want to know what the normal reaction force is equal to, I'm just going to add these components again. And these are the components of the weight. I've got the component of the weight that goes into the slope and a component of the weight that goes down the slope. Now, hopefully you can see here, the normal reaction force isn't equal to the weight, it's equal to mg cos theta, the weight times cos theta, because it's just one of the sides on this triangle. Now notice, you might be saying, theta, well, what's the angle here? Right down the bottom here, this is the slope angle, 18.9 degrees on this slope. Now this 18.9 degrees is also the angle at the top here between mg and mg cos theta. Okay, these are going to be the same angles. Okay, so whatever this angle is of the slope, it's also going to be this. So in general, if you know the slope angle, okay, then the component of the weight going into the slope is always going to be mg cos theta. Okay. Now you also notice the component of the weight going down the slope is mg sine theta. Okay, so remember, if one component is cos theta, the other is always sine. Now at the moment, this looks to me like it's balancing the frictional force. And you look, if I start with 0 and I move it up, these two forces, friction and mg sine theta, are balanced only up to a point, because there'll come a point where the static friction can't match mg sine theta anymore. And you notice here now, mg sine theta is getting bigger, but the static friction isn't. Now at this point, the object would no longer be stationary and it would start to move down the slope. Okay, and as it does move down the slope, in fact, on here you can actually press run and you'll see that the object will start to accelerate down the slope. Okay, so up until that point here, okay, the two forces are balanced. The static frictional force could balance the component of the weight down the slope, and if I press run, nothing happens. Okay, but as I make this angle bigger and bigger and bigger, eventually it slips off down the slope because the frictional force can't match mg sine theta. Okay, how can I alter the size of these forces? Well, there's a few things I can do. One thing I can do is I can muck around with the coefficients of friction. So if I made the coefficient of static friction much bigger, remember that the smallest it can possibly be is 0, basically means no friction. The largest it can possibly be is 1. If it's got a coefficient of 1, it means the frictional force is equal to the normal reaction force. So whatever the normal reaction force is, the frictional force will be the same. Okay. What I should have as well, remember, is static friction should always be bigger than the dynamic, or they put K for kinetic friction here. Okay, so you notice if I put the kinetic friction all the way up to the top, the biggest they'll let it go is the same as the static friction. Okay, so I could alter my static friction here. If I make this bigger or smaller, notice what happens to the frictional force. Okay, the frictional force changes depending on my coefficient, and that coefficient, remember, depends on the nature of the surfaces. Okay, it depends on the nature of the block itself and of the surface it's sitting on. The other thing I can do is I can change my mass. If I change my mass, it makes the weight bigger, which makes the normal reaction force bigger, which has a knock-on effect on the friction as well. Okay, so hopefully you can get the idea here that as I change the size of this angle, the way that the forces are distributed changes. So if it's a 90-degree angle, there isn't even a normal reaction. There's nothing to push back. Okay, so there's only the weight. If it's a 0 degree, we get a weight and normal reaction. But for any other angle, I get free forces, I get friction, normal reaction, and the weight. And the key thing that I want you to get out of this is that the normal reaction is not equal to the weight, except on a horizontal surface. On any other angle, okay, the normal reaction is equal to mg cos theta. Okay, and if the friction will be equal to mg sine theta, okay, as long as it's still stationary, or if it's moving at a constant speed. Basically, if it's in translational equilibrium, that means 0 resultant force, okay, then these two will be equal. But that doesn't always have to be the case. You see here, okay, at this point, I've made the component of the weight down the slope much bigger than the friction could possibly be. So these two are not going to be equal here. Okay, this object's going to accelerate. But if the object is staying at a constant speed or stationary, then we can say that these two are equal. Okay. Notice the language I use as well. I call this the component of the weight down the slope, and I call this the component of the weight into the slope. So mg sine theta is the component of the weight down the slope, okay, which will be equal to the frictional force while the object is stationary. And mg cos theta is the component of the weight into the slope, and that's equal to the normal reaction force. Okay, it's always equal to the normal reaction force. Otherwise, the object would move into the slope or into the air. So I'm going to post the link to this kind of simulation onto Google Classroom. You can have a fiddle around with this yourself, because I think it can be helpful sometimes just to play around and see things. But for now, I just want to continue with the PowerPoint I was on before. I'm going to have to wait a minute again because for some reason my computer's not responding very quickly when I'm on Screencastify. So I'm going to just do a little bit of maths with you to show you that actually if you change the angle of an object on a slope and you keep making it steeper and steeper, obviously at some point the objects are going to move, they're going to slip. So you put a book on a piece of wood. As you lift that piece of wood up, at first the object stays there, but eventually it's going to fall. And I'm going to get us to calculate the angle at which it will slip in a moment. Okay, but just before we do, these are the key forces that are involved here. So we've got N, which stands for the normal reaction. It's always perpendicular to the surface. Mg is the weight, which always acts towards the center of the Earth. And then these two, mg sine theta and mg cos theta, are just my components of the weight. Mg cos theta will balance the normal reaction, and mg sine theta doesn't necessarily balance the friction, but if it does, then it will be stationary. It could be that it's greater than the friction, and in that case, the object's going to accelerate down the slope. So on an inclined plane, the normal reaction force will not be equal to the weight. Okay, it will be equal to the component of the weight into the slope, mg cos theta. Okay, if the object is in translational equilibrium, that means zero resultant force, balanced forces, then the friction, should come up now, okay, will be equal to the component of the weight that acts, oh, I've said into the slope, that shouldn't say into the slope there, that should say the component that acts down the slope. Okay, right, let's do some maths with this. I have to move my, okay, so same things are drawn up on here, okay, and what I want to do from this is we're going to go through what I call a derivation, which is a little bit of maths to basically prove something. So the frictional force we know already is equal to the coefficient of friction times the normal reaction force. Okay, now the normal reaction force is mg cos theta because it's got to be equal to the component of the weight going into the slope, which is mg cos theta. Okay, now just as I do this, remember I've got to be careful which coefficient I use. At the moment, I'm going to assume that this object is stationary on the slope, okay, because I'm going to look at how far I have to tilt the slope before it starts to move. So I'm going to say at the moment I'm using static friction because I want the object to be stationary up to the point at which we've made the slope so steep that it can't be stationary anymore and it starts to slip. So the frictional force is equal to mu s times r, and r is equal to mg cos theta. Now, we also know that the component of the weight acting down the slope is mg sine theta. Okay, so we know mg sine theta is the force pushing down the slope. Now we know what the friction is up the slope. That's mu s mg cos theta. So we can say that when the weight down the slope, mg cos theta, is balanced by the friction up the slope, we're going to get this. Okay, my top line, mu s mg cos theta, is equal to my second line, mg sine theta. Okay, so this is when it's in equilibrium, where the object is either stationary on the slope or it's moving at a constant speed down the slope. Now, what we can do is rearrange this equation for mu s. So we can take mg cos theta and move it onto the other side. So we're going to divide mg sine theta by mg cos theta. The two mg's cancel. So I get mu s is equal to sine theta over cos theta. I don't know about how much maths you've done, but sine theta divided by cos theta is equal to tan theta. So we managed to simplify this down to that the coefficient of static friction is actually equal to the tan of the angle. Okay, and I'm going to reverse it. I'm going to say the object is going to slip and start to move if, well, I'm just going to do the inverse of the coefficient of static friction and say that the angle at which the object slips, okay, It will only slip if the angle is greater than or equal to the inverse tan of mu s. So this basically means if you know the coefficient of static friction, okay, you can work out the angle at which it will slip at. Okay, there's no other variables involved in it. So if you lift something up, like a slope up, okay, you can calculate the angle at which the object will slip as long as you know mu s. Or this can more often works the other way around. If you want to find the coefficient of static friction for an object, you put it on a slope, you lift the slope up, and when it starts to slip, you measure that angle, and you can use that angle to work out mu s. Okay, so I just wanted to show you that bit of maths. Now, I'm going to get you guys to do a bit of problem solving using kind of the friction ideas we've just talked about. Okay, as I said, these things are quite tricky. Okay, now I've posted on Google Classroom some friction past exam questions. Okay, there's a few different things they want you to do on it: draw a free body diagram, do some calculations of the frictional force, a bit of motion stuff as well, determining the acceleration of a block down the plane. Some things related to the frictional force action on them. This one here is particularly tricky about the friction on a person who's going round on a fairground ride, but I can get you to have a go at it. And then there are 3 multiple choice questions at the end as well. So what I would like you to do is to answer these. I mean, you can print them off and answer it on it, or you can just write your answers straight onto a sheet of paper. If you can then upload your answers so I can have a look at them. I'm not actually going to mark these ones. I just want to see that you've done it, and what I will do then is I'm going to release next lesson the official kind of IB mark schemes for these to you, because these are all questions that were on our old IB exams. So these are paper 2 questions, the first one where there's like a longish answer and calculations, and then the last 3 are paper 1 multiple choice questions. So I'll show you the answers next lesson, but for now I just want to see that you've made a decent attempt at it before I give you the answers. Okay, so if you've got any questions, please send me an email or write your questions onto Google Classroom, and I will get back to you as soon as I can on that. Thank you.